Okay, so just as the last video ended, we were about to do an example. So in the example, you would be told to use the mass of the proton as 1.007825 U's and the mass of the neutron 1.008665 U's. And just what I was saying at the end of the video is, depending on the book or the website you use, these might be a little bit different from each other. So always use the ones they tell you and don't always use the one that you think you know. It's all about rounding and how it's arrived at, but it'll be, so use the one that you're given in the particular question that you're doing. So in this question, it's telling us to use these masses, and it tells us the mass of the nucleus of the radioactive hydrogen. So this is the mass of the nucleus is 3.0, oops, sorry, my hand's in the way there, 3.0, 160, I don't know where to put my hand so it doesn't make a glare, 16049 U's. Now you got to be careful about rounding here. Look at how many decimals you have. So don't be rounding to one decimal place or two, right? Look at how many we have here. 3, 6, you're given 7 significant digits. So make sure that you're not rounding to 2. All right. So we're doing this for the mass. We're doing this for hydrogen 3, 1. Okay? So let me do it down here. So we know the mass defect. Okay, so you can write this as m dot d dot if you want. Actually, you can also write it as delta m if you want, the change in mass. And it's going to be equal to the mass of the nucleus minus, brackets, the sum of the masses of the neutrons plus the sum of the masses of the protons. Okay, and the delta works because the nucleus would be the final, these guys would be the initial. Remember, delta is always final minus initial. So the mass of the nucleus we were given is 3.016049 U's minus, there are 2 neutrons in hydrogen, so brackets 2 times 1.00, good if I was on the screen then, 1.008665 U's plus, and there's only one proton, so 1.007825 U's. And it's sometimes the proton that changes, so your textbook often uses this one, that's why I'm using this one. So when you do this, you get a delta M, so the first term is just going to be 0.16049. When you do the brackets, 3.025155. And so the answer you get here, if my hand would stop causing a glare, is negative 0.009106. Okay? What does the negative mean? It means mass is missing, mass is lost. That's why it's called a defect. Okay, so that's part A, what is the mass defect? Part B would be what is the binding energy? And so to get the binding energy, just need to make it smaller so we can see, binding energy, if we wanted in electron volts, mega electron volts, then it's just the delta M times the 931.48 capital M, mega electron volts per U. So you can leave the negative on if you want, 009106 U's times 931.48 mega electron volts per U, and you'll end up with a negative 8.4820568 mega electron volts, where again the negative means mass missing, which then means energy needed to be added. Now usually we leave the negative up here and we say what it is, and then when we get to this spot we drop our negative, okay? So, and then if you needed to go to find it in joules or kilograms, then you would convert your mega electron volts to electron volts, move the decimal 6 places, and then multiply by 1.602 times 10 to the negative 19 joules per electron volt, and that would give it you joules. And then you could do E equals mc squared. So take your joules, divide it by, right? So take your joules and divide it by the speed of light squared to get your mass in kilograms. Okay, so you could go use the conversion 1.602 to the negative 19 joules per electron volt, and that would give you your energy in joules, and then you could convert to kilograms, okay? But most often they want it in atomic mass units and mega electron volts. All right, so you're going to get to practice this in practice questions.